In the deep hush of a world grappling with uncertainty, it appeared. A silent traveller, emerging from the profound, unfathomable darkness between the stars. For a fleeting moment, in the summer of 2020, humanity, in its scattered and worried state, looked up together. They looked up to witness a ghost, a celestial pilgrim on a journey of billions of years. It was not an omen, nor a harbinger of cosmic tidings, but something far more profound. It was a messenger, a cryogenically preserved fragment from the dawn of our own existence. This was Comet Neowise, a whisper from the void, and it carried within its heart of ice and dust the secret recipe, not just for our world, but for countless worlds being born right now across the immensity of the cosmos, even in galaxies far beyond our own. To understand its message, we must first trace its extraordinary path. This object, designated C 2020 F3, did not simply wander into our neighborhood. Its journey was an epic of gravitational patience, a fall of unimaginable duration. It began its descent from a place so remote it strains the very definition of our solar system, the Oort cloud. Picture a vast, spherical shell of icy bodies, a cosmic seed bank encircling our sun at a distance of nearly a light year. This is not a belt or a ring, but a ghostly, diffuse sphere, the outermost frontier of the sun's gravitational influence. Out here, trillions of frozen relics from the solar system's formation tumble in a slow, silent ballet, barely tethered to our star. They are the leftover construction materials, the cosmic debris that never coalesced into planets. For eons, perhaps millions of years, this particular piece of ice and rock, no larger than a small mountain, drifted in the near absolute zero of interstellar space. Then, a subtle disturbance, perhaps the gravitational nudge from a passing star or a gentle tide from the Milky Way itself, dislodged it from its ancient, stable orbit. A cosmic apple had been shaken from the most distant branch of the solar tree. It began to fall inward, pulled by a force it had only ever felt as a faint whisper. The journey was long and solitary. It passed the orbits of phantom planets, cruising through a darkness punctuated only by the pinpricks of distant suns. For millennia, it fell, accelerating imperceptibly, drawn toward the growing warmth and light at the heart of the system. Its detection was a testament to our own relentless curiosity. It was first spotted not by a human eye at a telescope, but by an unblinking, infrared gaze in orbit around the Earth. The Near-Earth Object Wide Field Infrared Survey Explorer, or NEOWISE, is a space telescope with a singular mission: to scan the heavens for the faint heat signatures of asteroids and comets, the moving targets in our cosmic shooting gallery. On March 27, 2020, the automated systems of the telescope flagged a faint, moving smudge. An object, cold and dark, was betraying its presence through the faint infrared glow it emitted as it was warmed by the distant Sunday. At first, it was just another designation in a catalogue, another dot on a screen, but astronomers knew its trajectory was special. It was on a path that would take it perilously close to our star. This is the trial by fire for any long-period comet. As it plunged deeper into the inner solar system, the sun's energy began to work upon its ancient frozen surface. Ice that had been stable for 4.5 billion years started to sublimate, turning directly from a solid into a gas. This outgassing created a luminous, temporary atmosphere around the solid nucleus, a glowing shroud called the coma. This is what transforms a dark, inert mountain of ice into the beautiful, ethereal object we recognize as a comet. But this process is also violent and unpredictable. Many comets, like Icarus, fly too close to the sun and are ripped apart by the intense heat and gravitational forces. They disintegrate into clouds of dust and gas, their epic journey ending. In a silent, celestial fizzle, the astronomical community watched with bated breath as Neowise rounded the sun, its perihelion on July 3rd. Would it survive? It emerged from the solar glare, not only intact, but transformed. The sun's fiery breath had unleashed a spectacular display. Neowise now sported two magnificent tails, stretching for millions of kilometers across space. The first, a brilliant, bluish streamer of light, was the ion tail. It was composed of gases from the coma that had been stripped of electrons by the sun's ultraviolet radiation. This plasma was then caught and sculpted by the solar wind, a constant stream of charged particles flowing from the sun. Like a celestial windsock, this ion tail always pointed directly away from our star, regardless of the comet's direction of travel. The second tail, broad, curved, and luminously white, was the dust tail. This was made of larger particles, specks of rock and dust liberated from the melting ice of the nucleus. These heavier particles were less affected by the solar wind and more by the comet's own momentum, tracing a gentle arc along its orbital path. This tail was like a trail of cosmic breadcrumbs, marking the pilgrim's progress, and as it pulled away from the sun and climbed into the northern hemisphere's pre-dawn and post-dusk skies, it put on a show for the ages. Photographers, stargazers, and families ventured out into the darkness, away from the glare of cities, to witness this silent apparition. In a time of isolation, it offered a moment of shared wonder, a connection to something timeless and immense. It was a visceral reminder that our world is part of a much larger, dynamic, and ever-changing cosmos. But the true significance of this visitor lies not in its transient beauty, but in its composition. For this ghostly wanderer was a time capsule carrying the primordial chemistry of our solar system's birth. To understand the contents of this time capsule, we must travel back in time 4.6 billion years ago. Before the Earth, before Jupiter, before the Sun itself was a fully fledged star, there was only a vast, cold, dark cloud of gas and dust. A molecular cloud drifting through an arm of the Milky Way. Then, a shockwave, perhaps from a nearby supernova, a star's explosive death, compressed this cloud. Gravity took over, pulling the material inward. At the center, density and pressure skyrocketed. The core ignited with nuclear fusion, and our sun was born. What remained was a swirling, flattened accretion, disk of gas and dust, a protoplanetary disk. This was the cosmic nursery, from which everything else in our solar system would be made. Imagine this disk as a colossal, celestial construction site. In the hot, inner regions, only materials with high melting points, like rock and metal, could condense. These tiny grains stuck together through electrostatic forces and gentle collisions, growing from pebbles to boulders to planetesimals, and eventually to the rocky inner planets, Mercury, Venus, Earth, and Mars. Further out, beyond a demarcation line known as the frost line, it was cold enough for volatile compounds like water, ammonia, and methane to freeze into solid ice. This added a huge amount of building material to the mix. It allowed for the rapid growth of gigantic cores that swept up vast amounts of hydrogen and helium gas, forming the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. The process was messy, chaotic, and violent. Planetesimals collided, merged, and shattered. Gravitational interactions, especially from the behemoth Jupiter, flung material all over the system. Some objects were hurled into the sun, others were ejected entirely into interstellar space. And a vast number of smaller, icy bodies, the leftovers, the unused bricks from the construction site, were shepherded by the gravity of the giant planets into the two great reservoirs we see today, the Kuiper belt beyond Neptune and the far, far more distant Oort cloud. Comets like Neowise are pristine samples from that chaotic era. They are the deep frozen, unaltered remnants of the original solar nebula. Studying them is like a geologist finding a rock from the Earth's Hadean eon, perfectly preserved. It is a direct look into our own origins, and what we have found within them has revolutionized our understanding of the genesis of life itself. We once thought of comets as mere dirty snowballs, a term coined by astronomer Fred Whipple, but missions like the European Space Agency's Rosetta have revealed them to be astoundingly complex chemical factories. The Rosetta mission was an audacious feat of celestial mechanics. Launched in 2004, it spent a decade chasing comet 67P Churyumov-Gerasimenko through the solar system, performing intricate gravitational assists around Earth and Mars to match the comet's speed and trajectory. Finally, in 2014, it rendezvoused with its target, entering orbit around the strangely shaped duck-like nucleus. For 2 years, it was the comet's constant companion, watching it awaken as it neared the sun. Its lander, Philae, made a dramatic bouncing touchdown on the surface, giving us our first direct analysis from a comet's nucleus. The data sent back by Rosetta and Philae was breathtaking. Yes, there was water ice, but its isotopic signature, the ratio of heavy to normal water, was different from Earth's oceans, suggesting comets may not have been the primary source of our planet's water, though they certainly contributed. But more importantly, the probes detected a treasure trove of organic molecules, not just simple compounds like methane and carbon monoxide, but complex carbon-rich molecules, including several amino acids, the fundamental building blocks of proteins. They found glycine, the simplest amino acid, embedded in the comet's dust. They even found phosphorus, a key component of DNA, and molecular oxygen, a surprising discovery that hinted at chemical processes far more intricate than previously imagined. This discovery is the heart of the comet's message. It supports a profound theory known as panspermia, or more accurately, molecular panspermia. The idea is not that comets carry fully formed microbes, but that they act as cosmic delivery trucks. In the chaotic early days of the solar system, during a period called the Late Heavy Bombardment, Earth was relentlessly pummeled by asteroids and comets. This cosmic rain, which would be devastating to life today, may have been the very thing that kick-started it. These cometary impacts would have delivered 2 essential ingredients to the barren, primordial Earth: vast quantities of water helping to form the first oceans, and the complex organic molecules necessary for life to begin. The raw materials for the first cells, the amino acids, the carbon chains, were not synthesized in Earth's primordial soup, but were forged in the cold, dark nebula before Earth even existed, preserved in cometary deep freeze for hundreds of millions of years, and delivered, ready-made, to our nascent world. Comet Neowise, as it graced our skies, was a living embodiment of this process. Every particle of dust in its glowing tail was a microscopic packet of primordial chemistry, a potential seed for life. We were not just watching a celestial spectacle, we were watching our own origin story fly past. And this is where the narrative explodes, from our own backyard to the scale of the cosmos. If this is how our solar system was built, if the process of star and planet formation naturally creates and distributes the building blocks of life, then what does that imply when we look out beyond our sun to the hundreds of billions of other stars in our galaxy and the trillions of galaxies beyond? The journey of Comet Neowise becomes a guide, a local example of a universal phenomenon. It tells us not just how our world was formed, but how countless worlds are being formed right now across the universe. To see this process in action, we must turn to new eyes, telescopes of incredible power that can pierce the dusty veils of stellar nurseries. One of the most powerful is ALMA, the Atacama Large Millimeter Submillimeter Array. Perched high in the Chilean Andes, its 66 radio antennas work together as a single giant telescope capable of seeing the cold, dark universe where stars and planets are born. ALMA doesn't see the glittering light of stars. it sees the faint glow of coal dust and molecular gas. It can peer into the very protoplanetary disks we believe our solar system emerged from, and the images it has returned are among the most significant in modern astronomy. Consider the young star HL Tauri, located about 450 light-years away. When ALMA imaged its protoplanetary disk, it revealed something astonishing. The disk was not a smooth, uniform swirl of dust. Instead, it was marked by a series of distinct, concentric gaps, like the grooves on a vinyl record. Astronomers immediately realized what they were seeing. These gaps were being carved out by infant planets, protoplanets, sweeping up material as they orbited the star. For the first time, we were not just inferring the existence of planet formation. We were witnessing it. We were seeing, in real time, a solar system in the act of being born. ALMA has since found many such disks, each a snapshot of a different stage in the planetary construction process. We see spirals, clumps, and asymmetries, all signatures of the complex gravitational dance that builds worlds from dust. But the story gets even more compelling with the arrival of the James Webb Space Telescope, where ALMA shows us the structure of these disks. The JWST, with its unparalleled infrared sensitivity, can analyze their chemical composition. Using a technique called spectroscopy, the telescope can break down the faint light coming from these distant nurseries and identify the chemical fingerprints of the molecules within them. And what it is finding is a remarkable confirmation of our cosmic story. In the swirling disks around distant infant suns, JWST is detecting the telltale signs of water vapor. It is finding carbon dioxide, methane, and ammonia. It is finding the exact same volatile ices and simple organic precursors that we find locked away in the nucleus of a comet like Neowise. The implications are staggering. The chemical ingredients for worlds like ours are not rare or special. They are ubiquitous. The molecular cloud that formed our sun was not unique. These clouds, laden with water and carbon, are the standard starting material for stars throughout the galaxy. The process of forming a solar system appears to be a robust and common outcome of star formation, and that process naturally creates icy reservoirs, Oort clouds, Kuiper belts filled with comets. These comets in turn act as a delivery system, seeding their young, rocky planets with water and organics. The entire sequence of events that led to a habitable, life-bearing Earth is not a bizarre fluke, but is seemingly written into the fundamental laws of cosmic chemistry and physics. The script is the same, only the stages and actors are different, and so we must take the final, mind-bending leap proposed by our initial inquiry. If this is happening to stars in our galactic neighborhood, what about worlds forming in another galaxy? From our vantage point, other galaxies are faint, ethereal islands of light. The Andromeda Galaxy, our closest large neighbor, is a majestic spiral visible to the naked eye as a faint, fuzzy patch. It is over 2.5 million light-years away. Resolving individual protoplanetary disks within it is currently far beyond the capability of any telescope we have built. We cannot zoom in on a single alien HL Tauri in the spiral arms of Andromeda, but we don't need to. We can study these galaxies in aggregate. When we point our most powerful telescopes at the great star-forming regions within Andromeda, the vast glowing nebulae where thousands of stars are being born at once, the light we receive is the combined light of all those infant solar systems. The spectroscopic signals tell us that the chemistry at play is identical. The same hydrogen, the same helium, the same carbon, oxygen, and nitrogen forged in earlier generations of stars are present there. The same vast molecular clouds are collapsing. The same physical laws are governing the formation of stars and their accompanying disks. There is absolutely no reason to believe the process would be any different. The universe, for all its variety, is remarkably consistent. So, while we cannot see the specific gaps in a specific disk in another galaxy. We can say with a high degree of scientific confidence that it is happening. As you read this, in the Triangulum galaxy, a young star is igniting, and the remnants of its birth cloud are flattening into a disk. Within that disk, dust grains coated in water ice and organic molecules are sticking together. In the Sombrero galaxy, a Jupiter-sized planet is carving a great canyon through its natal nebula, flinging icy comets into the outer reaches of its system. Billions of years from now, some of those comets may fall inward, delivering their life-giving cargo to a young, rocky world. The formation of worlds is not just a feature of the Milky Way. It is a feature of the cosmos. It is happening in every galaxy that has enough gas and dust to form new stars. It is a continuous, universal process of creation. This realization forces us to confront some of the deepest questions of our existence. If the building blocks for life are universal, and if the process for assembling them into habitable planets is common, then where is everybody? This is the famous Fermi paradox. The universe should, by all accounts, be teeming with life, yet we are met with a profound silence. Perhaps life is common, but intelligent life is rare. Or perhaps intelligent, life inevitably destroys itself. Or maybe the distances are just too vast, and we are isolated in a cosmic ocean, unable to hear the calls of others on distant shores. But the message of the comets offers a more hopeful perspective. It suggests that the potential for life is everywhere. The universe is not a barren, hostile void with one lucky exception. It is a fertile cosmos, constantly planting the seeds of possibility. Our existence is not a miracle, in the sense of being an impossible event. It is a miracle in the sense of being the magnificent, natural outcome of 4.5 billion years of cosmic, geological, and biological evolution, a process that was kick-started by the delivery of primordial material from icy messengers. Our planet was seeded from the dust of the cosmos, a truth that connects us to every star-forming cloud in every galaxy. Let us return, finally, to that lone observer standing under the night sky, gazing up at the faint, ghostly streak of comet Neowise. The sight is no longer just a beautiful, transient event. It is a profound connection to the deepest history and the grandest future. That comet is a piece of the very same cloud that gave birth to the Earth, the Sun, and to us. The carbon atoms in the observer's body were forged in the heart of a long-dead star, ejected into space, mixed into a molecular cloud, and delivered to a young Earth by an object just like the one they are witnessing. The water in their veins may have travelled for eons through the cold of space, locked in the heart of a dirty snowball. And as that comet's dust tail spreads microscopic particles across our planet's orbit, particles we will pass through for centuries to come as meteor showers, it is a reminder of this cosmic heritage. That dust is the same kind of dust that is, at this very moment, clumping together around a newborn star in the Orion Nebula. It is the same kind of dust that is swirling in the vast disks of Andromeda, slowly, patiently, building new worlds. The journey of one comet illuminates the creation of trillions of planets. Its fleeting passage through our sky connects our personal, terrestrial existence to the grand, universal narrative of cosmic creation. It is a messenger that tells us we are not separate from the universe, but a fundamental expression of it. We are the children of the stardust delivered by the ice, and our story is just one verse in an epic poem that is being written across the galaxies, world without end. What if the most complete picture of reality we have ever captured, a photograph of the universe in its infancy, contains a chilling, deliberate flaw? Imagine a perfect, seamless map of the early cosmos, a testament to our theories and our understanding of everything, but with one vast, inexplicable continent of cold, where there should be uniformity. Every origin story has its first light. For our universe, that light is not the brilliant flare of a star, but a faint, persistent whisper, echoing through the 13.8 billion years since the dawn of time. We call it the cosmic microwave background, the CMB. It is not light you can see with your eyes, but rather a ghostly thermal afterglow from the moment creation cooled enough for light to finally break free from the plasma prison of the Big Bang. For 380,000 years, the cosmos was an opaque furnace, a seething soup of particles and radiation bound together in an impenetrable fog. Then, in a moment of cosmic transfiguration, the universe expanded and cooled just enough for atoms to form. Light for the very first time had a clear path to travel. That first light stretched by cosmic expansion over eons into the microwave spectrum is what we see today when we point our most sensitive instruments to the heavens. It is without exaggeration the most profound artifact in all of cosmology. This ancient radiation bathes the Earth from every direction, a near perfectly uniform glow with a temperature just 2.7 degrees above absolute zero. It is a baby picture of the universe, a fossilized record of the conditions that existed when the cosmos was a mere infant. In its subtle, almost imperceptible variations in temperature, we can read the story of our own origins. These tiny fluctuations, minuscule ripples in the fabric of space-time, were the primordial seeds of creation. They were the gravitational anchors around which all the magnificent structures we see today, the galaxies, the clusters, the great walls of shimmering stars, would eventually coalesce. For decades, our understanding of the universe, our entire standard model of cosmology, has been built upon the foundation of this image. The model predicted this background radiation with astonishing accuracy, and its discovery was a triumphant validation of our theories. It tells us that the early universe was remarkably homogeneous, incredibly smooth, with the same properties in every direction we look. It is a portrait of cosmic tranquility, a confirmation that the laws of physics as we understand them have held true since the very beginning. But this portrait of cosmic infancy is not perfect. It is haunted by a ghost. Hidden within that gentle uniform warmth lurking in the southern sky in the direction of the constellation, Eridanus is something that should not be there. It is a wound in the fabric of the early universe, an anomaly so vast and so profound, it challenges the very foundations of our cosmic model. We call it, with a simplicity that belies its terrifying implications, the CMB cold spot. Discovered by NASA's Wilkinson Microwave Anisotropy Probe, and later confirmed with even greater precision by the European Space Agency's Planck satellite, this region is a sprawling expanse of unusual cold. It is a blemish on the otherwise pristine face of the infant cosmos. Now, the temperature variations across the CMB are incredibly small, measured in millionths of a degree. They are the gentle hills and valleys of the primordial universe, but the cold spot is different. It is not a gentle valley, it is a chasm. Spanning more than 1 billion light-years of space on our sky, this region is significantly colder than the average, a deviation far greater than the standard subtle fluctuations that speckle the rest of the map. To grasp the scale of this anomaly is to confront the limits of our cosmic perspective. If you were to hold your arm out to the night sky, the patch covered by the cold spot would be many, many times the size of the full moon. It is a colossal shadow, an island of profound cold in an otherwise temperate sea. The chances of such a large and intensely cold region appearing by pure random fluctuation as a simple statistical fluke in the otherwise uniform glow of the CMB are staggeringly low. Depending on the statistical model you use, the odds are something like 1 in thousands, perhaps even 1 in 100,000. Imagine flipping a coin and having it land on heads 1,000 times in a row. You wouldn't just assume it was chance, you would begin to suspect the coin was weighted. The cold spot is that weighted coin. It is a signal that something is fundamentally amiss in our understanding. It is a cosmic outlier of the highest order, a deep resonant note of dissonance in the otherwise harmonious symphony of the Big Bang. It sits there in our data stark cold and silent, asking us a question we cannot yet answer: what created it? What could possibly have the power to carve out such a monumental chill from the very dawn of time? This is not merely an academic puzzle. It is a direct assault on the central pillar of modern cosmology, the principle of isotropy. This principle, a core tenet of our standard model, posits that the universe on its largest scales looks the same in every direction. There are no special places, no preferred axes, no great cosmic signposts that say, "You are here." The universe should be, for lack of a better word, uniform, and for the most part it is. The distribution of galaxies, the expansion of space, and the temperature of the CMB are all remarkably consistent no matter where we look. This uniformity is what allows us to create universal laws to believe that the physics we observe here on Earth applies everywhere across all of space and all of time. But the cold spot violates this principle in the most dramatic way imaginable. It is a special place. It is a unique feature, a gargantuan structure that breaks the elegant symmetry of the cosmos. Its existence suggests that our master theory of the universe, the grand narrative we have constructed over a century of observation and calculation, might be incomplete. It might even be wrong. The implications are profound. If our standard model cannot account for such a prominent feature in its own baby picture, what else might it be missing? What other secrets are hidden in the dark, waiting to dismantle our neat and tidy view of reality? For years, cosmologists wrestled with this phantom. The first, most obvious explanation was instrumental error. Perhaps the satellites that mapped the sky were flawed. Perhaps this cosmic chill was nothing more than a glitch in our own technology, a smudge on the lens of our cosmic telescope. But as new, more powerful instruments were brought to bear, the cold spot refused to vanish. In fact, with each successive observation, its existence was only solidified, its features mapped with ever greater and more unnerving clarity. It was undeniably real. The next possibility was that it was simply an improbable, but not impossible roll of the cosmic dice, a statistical fluke. After all, in an infinite or near-infinite universe, even the most unlikely events are bound to happen somewhere. Perhaps we just happen to live in a corner of the cosmos where we are looking out at a 1 in 100,000 anomaly. But for many scientists, this explanation is deeply unsatisfying. It feels like an abdication of the scientific quest, a surrender to sheer coincidence, rather than a search for a physical cause. Science seeks mechanisms, not miracles. And so the hunt began for a physical explanation for some tangible, undiscovered phenomenon that could account for this immense celestial bruise. The search forced astronomers to look not just at the distant past, at the light from the CMB itself, but at the vast intervening space between us and that ancient glow. The light from the dawn of time has travelled for 13.8 billion years to reach us. Its journey has been epic, traversing a cosmos that has been anything but empty. It has passed through colossal filaments of dark matter, skirted the gravitational whirlpools of galaxy clusters, and crossed billions of light-years of expanding space. What if the chill isn't a feature from the beginning of time at all? What if instead it's an illusion, a shadow cast not by something present at the dawn of the universe, but by something absent in the universe of today, an optical trick created on the light's long journey to our telescopes? This radical idea shifted the focus from the Big Bang to the very structure of the modern cosmos, to the great unseen architecture that matter has formed over billions of years. We know that galaxies are not scattered randomly through space. They are woven into a magnificent shimmering tapestry known as the cosmic web. In this web, galaxies are strung along immense filaments of dark matter, gathering at dense intersections to form massive clusters. But between these glittering threads of matter lie the great voids. These are the forgotten spaces of the universe, the cosmic deserts. They are incomprehensibly vast regions of near-total emptiness, caverns of nothingness, stretching for hundreds of millions, sometimes even billions of light-years. They are not perfect vacuums, but their density of matter is a tiny fraction of the cosmic average. They are places where the relentless pull of gravity has swept the surroundings clean, leaving behind an immense gravitational valley. We call the very largest of these structures supervoids. They are the great silent counterparts to the bright, bustling superclusters of galaxies, and in their profound emptiness, scientists began to see the faint outlines of a new and extraordinary explanation for the cold spot. The theory is both elegant and deeply counterintuitive. It relies on a subtle interplay between gravity light and the accelerating expansion of the universe, a phenomenon driven by the mysterious force of dark energy. Imagine a photon of light from the cosmic microwave background beginning its journey towards us billions of years ago. As it approaches a supervoid, it enters a region of lower than average gravity. It's like rolling a marble down into a shallow bowl. The photon falls into the gravitational valley, and in doing so it gains energy. This causes its wavelength to shorten slightly, a process known as a gravitational blue shift. The light gets a tiny bit hotter. In a static, unchanging universe, the story would end there. As the photon climbed back out of the gravitational valley on the other side, it would lose the exact same amount of energy it gained on the way in. It would be redshifted by a corresponding amount, and its temperature would return to normal. The net effect would be zero. The void would be invisible. But our universe is not static. It is expanding, and that expansion is accelerating. While that photon is traversing the hundreds of millions of light years across the supervoid, the universe itself is stretching. Dark energy is pushing everything apart, causing the void to grow and become even shallower. By the time the photon is ready to climb out, the gravitational hill it must ascend is flatter and less steep than the one it rolled down. It therefore loses less energy climbing out than it gained falling in. The result is a net energy gain, meaning the light should actually appear slightly hotter after passing through a void. But there's another more dominant effect at play in certain models, an integrated effect of the void's passage. As the light travels through the stretched, emptying void, it loses energy to the cosmic expansion. The gravitational potential of the void itself is changing over the transit time. The light has to work against the expansion to escape, and it emerges with less energy than it had when it entered. It has been taxed by its journey. This loss of energy registers as a slight drop in temperature, a redshift. The light is made colder. A single small void would have a negligible effect, far too tiny to notice. But what if there were a truly colossal structure, a supervoid of unprecedented scale, an emperor of voids positioned perfectly along our line of sight to that particular patch of the CMB? Such a structure, a monumental gravitational pothole in the fabric of space-time, could potentially force the ancient light passing through it to lose just enough energy to create the anomaly we observe. It would mean the cold spot is not a primordial feature from 380,000 years after the Big Bang. It would be a foreground mirage, a gravitational lens of immense proportions distorting our view of creation and masquerading as a cold spot from the dawn of time. Could this be the answer? Could this cosmic phantom, this gaping wound in our sky, be explained by an equally gaping hole in the universe itself? Is there a colossal supervoid, a titan of emptiness lurking in the dark between us and that ancient light? The search was on not for a complex new theory of physics at the dawn of time, but for a hole in the universe today. Astronomers began to peer deep into the darkness of the Eridanus constellation, meticulously mapping the three-dimensional distribution of galaxies, searching for the telltale absence of matter that would betray the presence of a supervoid. What they would find would not only deepen the mystery of the cold spot, but also reveal the shocking skeletal structure of our local universe, forcing us to confront the true scale of the cosmic web and the profound emptiness that defines it. There is a map not of continents or oceans, but of time itself. It is the oldest, most profound, and most complete picture of our universe that we will ever possess. This is not an image painted with the familiar light of stars or galaxies, but with a far more ancient glow, a phantom radiation that saturates all of space. It is the cosmic microwave background, the faint persistent ember of the Big Bang. To look upon this map is to witness the cosmos as it was just 380,000 years after its violent birth, a mere infant in cosmic terms. It is our universe's first photograph captured at the precise moment the primordial fog cleared, and light was set free to travel unimpeded for the next 13.8 billion years. This fossil light carries within it the seed code of everything that would ever exist. Every star, every galaxy, every planet, and even you are descended from the patterns encoded in this ancient whisper. When we first detected this radiation, a faint unwavering hiss of static discovered by accident in 1964, it appeared almost perfectly uniform. A constant near absolute zero temperature of 2.7 Kelvin, no matter which direction we pointed our antennas. This uniformity was itself a staggering revelation. a confirmation that the universe truly did begin in a hot, dense state. It was the echo of creation. But the true story, the grand narrative of cosmic evolution, was not written in the uniformity. It was hidden in the imperfections. As our instruments grew more sensitive, capable of discerning temperature variations of less than 1 part in 100,000, a breathtaking new panorama was revealed. The map was not a flat, featureless monotone. It was a stunning tapestry of infinitesimal warmer and colder patches, a mottled pattern of cosmic highs and lows scattered across the entire celestial sphere. These are not random smudges on a cosmic lens. They are the most important features in the universe. The slightly warmer, denser regions represent the primordial seeds of structure. These were the gravitational wells, the cosmic cradles, where matter would first begin to pool, drawn together by its own immense gravity over hundreds of millions of years. Within these gentle hollows, the first stars would ignite, bathing the young cosmos in light. The first galaxies would coalesce, swirling into majestic spirals. And from those galaxies, clusters and superclusters would form, weaving the vast, intricate cosmic web we see today. The slightly cooler, less dense regions in turn would give rise to the great voids, the colossal deserts of near-nothingness that separate the glittering filaments of galaxies. This map, this echo of the past, is therefore also a prophecy. It is a blueprint containing the precise initial conditions from which the entire magnificent structure of the modern universe would ultimately unfold. We had in our hands the architectural plans for reality itself. To understand this blueprint, to read its cryptic language cosmology, devised its own grand theory, a powerful and elegant model that has become the bedrock of our understanding. We call it the lambda-cold dark matter model, or lambda CDM for short. It is far more than just a theory. It is our standard story of the cosmos, a comprehensive narrative that explains how we went from the smooth hot plasma of the early universe to the complex star-filled cosmos we inhabit. For decades it has been triumphantly successful, predicting the universe's properties with astonishing accuracy. Lambda CDM is built upon a few key, albeit mysterious, pillars. The first is a concept that defies all terrestrial intuition inflation. The model proposes that in the first fleeting fraction of a second after the Big Bang, the universe underwent a period of hyperacceleration, an exponential expansion of unimaginable violence and speed. In less than the blink of an eye, a region of space smaller than a proton swelled to become larger than a galaxy. This incredible event, a cosmic masterstroke, solves several deep cosmological puzzles at once, primarily explaining why the universe is so vast and so geometrically flat. But for our story, its most profound consequence was what it did to the quantum world. In the subatomic realm, reality is a fizzing energetic foam of uncertainty, where particles and energy fields constantly fluctuate in and out of existence. Inflation took these microscopic quantum jitters and stretched them, magnifying them to astrophysical scales. Tiny fleeting ripples in the primordial energy field were expanded into vast gentle waves. It was these inflated quantum fluctuations that became the very seeds of structure we now see imprinted on the cosmic microwave background. Inflation set the stage, drawing the initial sketches on the cosmic canvas. But for those sketches to develop into the rich tapestry of galaxies we see today, another more enigmatic ingredient was required. Lambda CDM posits the existence of cold dark matter, a mysterious invisible substance that interacts with the universe almost exclusively through gravity. It does not emit, absorb, or reflect light. It is a ghost passing through us, through planets, and through entire stars as if they were not there. Yet according to our models, it outweighs all the normal visible matter, the stuff of stars and gas and people. By a factor of more than 5 to 1, it is the universe's silent majority. During the era of the CMB, this dark matter had already begun to clump together, its immense gravitational pull creating the very scaffolding upon which the visible universe would be built. The tiny density variations in the primordial plasma were not strong enough on their own to overcome the outward pressure of radiation. Normal matter needed a gravitational anchor, a pre-existing cosmic framework to fall into. Dark matter provided that framework. It was the unseen architect shaping the cosmic web, dredging the great basins of space-time into which galaxies would eventually settle. Without dark matter, the seed seen in the CMB would have remained just that seeds dispersed and unable to sprout into the magnificent structures that populate our universe. The model paints a picture of a gravitational dance on a cosmic scale, where the visible follows the invisible, and the grand design of the cosmos is dictated by a substance we cannot see and do not yet understand. And finally, the model's name gives us its last and perhaps most perplexing component, lambda, the cosmological constant more commonly known as dark energy. If dark matter is the cosmic architect pulling things together, dark energy is the relentless force pushing everything apart. It is a strange, repulsive energy woven into the very fabric of space-time itself, causing the expansion of the universe not to slow down as one might expect from gravity's pull, but to accelerate. It is a phantom pressure, a cosmic anti-gravity, that began to dominate the universe's evolution some 5 billion years ago. Today, it is the most powerful force in the cosmos, on the larger scales accounting for nearly 70% of the total energy density of the universe. Its existence means our cosmos is destined not for a fiery big crunch, or a quiet equilibrium, but for a big freeze, a future where galaxies are pushed so far apart that the sky as seen from any one of them will eventually become cold, dark, and utterly empty. Together, these three pillars, inflation, cold, dark matter, and dark energy, form the lambda CDM model. It is a cosmic recipe. Take a pinch of normal matter, add a generous helping of dark matter, and let it expand and cool according to the known laws of physics, then season with a dominant dash of dark energy to drive accelerating expansion. This recipe doesn't just tell a compelling story, it makes precise, falsifiable predictions. Crucially, it predicts the statistical nature of the map of the cosmic microwave background. It tells us exactly what kind of patterns we should expect to see. The model dictates that the hot and cold spots should be distributed randomly, or what physicists call Gaussian. There should be no preferred direction in the sky, no special features that stand out against the background of random noise. It predicts a specific spectrum of sizes for these spots, with a characteristic scale of about 1 degree on the sky being the most common. For years, as our technology improved, our observations seemed to match these predictions with breathtaking fidelity. Our cosmic model was a masterpiece of scientific achievement. The data from our satellites confirmed its predictions again and again. It was a symphony of cosmic harmony, a perfect union of theory and observation. The universe, it seemed, was behaving exactly as it should. And then we looked closer. Our quest for precision led us to build extraordinary instruments, cosmic cartographers launched into the cold vacuum of space, far from the distorting haze of Earth's atmosphere. The first was NASA's Wilkinson Microwave Anisotropy Probe, or WMAP. Launched in 2001, it spent 9 years patiently staring into the dawn of time, mapping the CMB with a sensitivity and resolution that dwarfed all previous efforts. WMAP's data was a triumph, refining our knowledge of the universe's age, its composition, and its geometry. The map it produced was a thing of beauty, its patterns aligning almost perfectly with the predictions of lambda CDM. Almost. As scientists meticulously analysed the data filtering out the foreground glare from our own Milky Way galaxy, they began to notice something peculiar. In the southern celestial hemisphere in the direction of the constellation Eridanus, there was a patch of the sky that seemed off. It was a region of unusual coldness sprawling across a vast expanse of the ancient sky. At first, it was dismissed as a statistical fluke, a random artifact in the data, or perhaps an error in the complex process of subtracting galactic foregrounds. The universe is a messy place, and making these maps is an exercise in painstaking cosmic archaeology. But the feature persisted. It was there, stubbornly refusing to disappear. Then came the European Space Agency's Planck satellite, an even more powerful and sensitive instrument launched in 2009. Planck's mission was to create the ultimate map of the primordial universe, to measure the CMB's temperature variations with such exquisite precision that it would push the lambda CDM model to its absolute limits. If there were any cracks in our standard model of cosmology, Planck was designed to find them, and it did. When Planck delivered its data, the new map was sharper, clearer, and more detailed than ever before, and there in the same patch of sky was the anomaly now rendered in undeniable high definition. The CMB cold spot was real. What makes this feature so deeply troubling is not just that it's cold. The CMB is by its very nature a tapestry of hot and cold spots. The issue is its sheer size and its profound coldness combined. This is not a subtle deviation, it is a glaring outlier. Spanning more than 10 degrees across the sky, 20 times the width of the full moon, it is significantly larger and colder than any of the other features on the map. It is a cosmic bruise, an inexplicable chill in the otherwise warm glow of the newborn universe. In the context of the lambda CDM model, which predicts a random Gaussian field of fluctuations, a feature of this magnitude is a statistical improbability of the highest order. The precise odds are a matter of intense scientific debate dependent on the exact statistical methods used, but the conclusions all point in the same direction. The chance of such a spot forming from the random quantum fluctuations predicted by inflation could be as low as 1 in 1,000, or perhaps, as some more dramatic analyses suggest, less than 1 in 50,000. Imagine flipping a coin thousands of times and recording the results. You expect a random sequence of heads and tails, but what if in the middle of your experiment you get a run of 100 heads in a row? You would immediately suspect the coin is loaded. The CMB cold spot is cosmology's run of 100 heads. It is a feature so extreme that it strains the definition of a statistical fluke to its breaking point. It violates one of the most fundamental assumptions of modern cosmology, the cosmological principle, the idea that the universe on its largest scales is homogeneous and isotropic. It should look the same everywhere and in every direction. But the cold spot suggests otherwise. It suggests there is in fact a special direction in the sky, a place that is fundamentally different from all others. It stands as a profound and defiant anomaly, a phantom fingerprint on the otherwise pristine photograph of our infant cosmos. For years, cosmologists have grappled with this chilling puzzle. They have rechecked the data, rerun the simulations, and re-examined their own assumptions. Could it be an unknown systematic error in our instruments? Both WMAP and Planck, two completely different satellites with different instrument designs, saw the exact same feature in the exact same location. Could it be some strange foreground contamination from our own galaxy, or a nearby cluster scientists have meticulously modelled and subtracted every known source of microwave emission, and the cold spot remains? We are left facing a deeply unsettling possibility. This is not an error in our telescopes or a smudge on the lens. It is a real feature imprinted on the fabric of space-time itself, 13.8 billion years ago. And it is something our best, most successful theory of the universe simply cannot explain. The existence of the cold spot forces us to ask a question that strikes at the very heart of our cosmic understanding. Does this single anomalous feature signal the first crack in the magnificent edifice of the lambda CDM model? Are we seeing the first hint that our grand cosmic recipe is missing a crucial ingredient, or that our fundamental assumptions about the universe's birth are wrong? Perhaps inflation didn't happen the way we think it did. Or maybe the universe is not as simple as our models assume. Perhaps there are other more exotic physical laws at play, laws that could create such a colossal, cold imprint on the dawn of time. Or perhaps the explanation lies not in the distant past, not in the physics of the Big Bang itself, but somewhere much closer in the vast, dark and mostly empty universe that lies between us and that ancient wall of light. Could something be happening in the intervening billions of years of cosmic history to actively create this illusion of coldness? What if the light from that specific patch of the early universe has been travelling through something extraordinary, something immense and empty on its long journey to our telescopes? We stand at a precipice staring at a map of our own cosmic origins and find a feature that shouldn't be there. It's a clue, a mystery, a challenge etched into the oldest light in the universe, beckoning us to look deeper into the darkness. Undefined. And so, this unsettling blemish on the face of creation, this thumbprint of some unknown force, demands an explanation. Our search for its cause begins not by peering deeper into the past, but by turning our gaze to the vast intervening darkness that lies between us and that first light. The journey of a photon from the dawn of time to your eye is unimaginably long, a 13.8 billion year odyssey. Along that path, it is a silent witness to the entire evolution of the cosmos. It passes through the birth of the first stars, weaves between the gravitational tendrils of nascent galaxies, and traverses billions of light years of what we often and incorrectly call empty space. But space, we have learned, is not a featureless backdrop. It has a structure, a grand and intricate architecture. Imagine a three-dimensional web spun by a cosmic spider, where shimmering filaments of galaxies and dark matter stretch across the universe, connecting at brilliant dense knots. These knots are the superclusters, the great metropolises of the cosmos, teeming with thousands of galaxies blazing with the light of trillions of stars. The filaments are the galactic highways channeling matter and energy from one cosmic city to another in a slow, inexorable gravitational flow. It is a structure of breathtaking complexity and beauty. But this is only half of the story. For every glittering filament, for every radiant cluster, there exists an equal and opposite reality. Between the threads of this cosmic web lie the great vacancies, the colossal echoing chambers of near-nothingness. These are the supervoids. To call them empty is a profound understatement, a failure of human language to capture their sheer scale of desolation. A typical void might span 200 million light-years. The largest the supervoids can stretch for more than 1 billion light-years. Our own Milky Way galaxy, with its hundreds of billions of stars, would be less than a single grain of sand lost in a desert the size of a continent. These are regions so vast that light itself, the fastest thing in existence, takes 1 billion years to cross from one side to the other. They are cosmic oceans of profound underdensity, where the great tide of cosmic evolution has pulled all the matter away, leaving behind a silence and a solitude that is almost absolute. If you were to stand on a planet inside a supervoid, the night sky would be a terrifying perfect black. No Milky Way band, no neighbouring galaxies like Andromeda, perhaps only a handful of faint lonely star systems, each an isolated island in an endless sea of darkness. The grand cosmic conversation of gravity and light would be muted to a whisper. This is not the fertile vacuum from which universes spring, but a chilling terminal kind of emptiness. The existence of these voids is not a mystery. It is a direct and necessary consequence of gravity itself. To understand how they form, we must rewind the clock back to the moment that primordial light was first released, the very image we see in the cosmic microwave background. That ancient fireball was not perfectly smooth. Imprinted upon it were quantum fluctuations from the first instant of time, infinitesimally small variations in temperature and density. Some regions were 100,000th of a degree warmer, meaning they were a fraction of a percent denser than the average. Other regions were imperceptibly cooler, microscopically less dense. These tiny seeds of structure were all the universe needed. Gravity, the master sculptor of the cosmos, went to work. It is a force that plays a relentless game of the rich get richer. Those slightly overdense regions exerted a slightly stronger gravitational pull. They began to tug on the matter around them slowly, but surely reeling it in, growing denser still. Over millions and then billions of years, this process snowballed. The overdense patches became the gravitational cores of future galaxies. They pulled and pulled, collapsing into stars, merging into galaxies, and assembling themselves into the colossal clusters and filaments we see today. But for every action there is a reaction. As all this matter was being drawn towards these centres of gravity, it had to be pulled from somewhere. It was evacuated from the regions that started out just slightly less dense. These underdense regions, having lost what little matter they had saw, their gravitational influence weakened even further. They couldn't compete. They became the zones of cosmic exodus. As the filaments grew brighter and the clusters grew heavier, the voids between them were stretched, expanded, and hollowed out, becoming ever more vast and ever more empty. They are the cosmic valleys carved out by the gravitational rivers that flow towards the mountains of the superclusters. They are the proof written in emptiness across the sky that the entire structure of our universe grew from the tiniest of quantum seeds. So we have a suspect, a colossal region of intergalactic space, a supervoid conspicuously empty of galaxies. And we have a crime scene, a patch of the CMB sky that is unnaturally cold. For a long time, connecting the two seemed impossible. How could a void which is mostly nothing leave a mark on light that is just passing through it? The answer is one of the most subtle and beautiful effects in all of cosmology, a consequence of Einstein's general relativity playing out on the largest possible stage. It involves the journey of our ancient photon and its interaction with the very fabric of space-time. Imagine one of these CMB photons having travelled for billions of years, approaching the edge of a colossal supervoid. According to Einstein mass and energy bend space-time, a massive galaxy cluster creates a deep depression, a gravitational well. A photon falling into this well gains energy just as a marble rolling downhill speeds up. This energy boost manifests as a tiny shift towards the blue end of the spectrum. It gets hotter. As it climbs back out of the well on the other side, it has to fight against that same gravity, losing the exact amount of energy it gained. It gets redshifted back to its original temperature. In a simple, non-expanding universe, the net effect is zero. The photon leaves with the same energy it had when it arrived. A void, however, is the opposite. It is a region of underdensity. It has less mass, less gravity than the surrounding universe. It doesn't create a gravitational well, it creates a gravitational hill. As our photon approaches the void, it has to climb this gentle, invisible slope in space-time. To climb it must expend energy. This causes the photon to lose a tiny bit of its momentum, shifting its wavelength ever so slightly towards the red. It becomes colder. It then traverses the immense breadth of the void, a journey that might take 1 billion years. Finally, as it reaches the far side, it rolls down the other side of the gravitational hill. In that descent, it should regain the precise amount of energy it lost on the way in, being blue shifted back to its original temperature. Once again, the net effect should be zero. The void should be completely invisible to the photon. But this elegant symmetry is broken by the most mysterious force in the universe. It is broken by dark energy. This strange anti-gravitational influence, this intrinsic energy of space itself, is causing the expansion of the universe to accelerate, and this acceleration changes everything for our travelling photon. Let's replay the journey. The photon arrives at the edge of the supervoid and begins its long climb up the gentle slope of the gravitational hill, losing energy and cooling down. But while it is inside the void for the hundreds of millions of years it spends crossing it, the universe is not static. Dark energy is relentlessly pushing space-time apart. This cosmic acceleration stretches the supervoid itself, making it larger and crucially making its gravitational influence weaker. The gravitational hill is being flattened out even as the photon is climbing it. By the time our photon reaches the other side and begins its descent, the hill it is rolling down is now shallower than the hill it climbed to get in. The slope is less steep. The gravitational push it gets on the way out is weaker than the gravitational pull it had to fight on the way in, and so it does not regain all of the energy it lost. The transaction is no longer balanced. The photon leaves the supervoid with a tiny energy deficit. It emerges slightly redder, slightly colder than when it entered. This phenomenon, this cosmic energy tax imposed by dark energy, is known as the integrated Sachs-Wolf effect, or IKSW effect. It is an incredibly subtle signature, a whisper of dark energy's influence imprinted onto the oldest light in the universe. For any single void, the effect is minuscule, almost undetectable. But what if the void were exceptionally large? What if it were a supervoid 1 billion light-years across? And what if there were not just one, but a series of them aligned along our line of sight like bubbles in a cosmic flute? The tiny cooling effects would add up. Each void would shave off another fraction of a photon's energy, leaving it colder and colder with each passage. Suddenly we have a physical mechanism born from our most advanced understanding of the cosmos that could plausibly explain the CMB cold spot. The theory is breathtaking in its elegance. It proposes that the cold spot is not some exotic relic from the Big Bang, but a modern illusion and artifact of the photon's long journey. It suggests the light from that direction of the sky started out normal, just like the light from everywhere else. But on its way to us, it happened to pass through one of the largest, most desolate structures in the entire known universe. The cold spot, in this view, is the shadow of a colossal emptiness. It is the gravitational fingerprint of a supervoid, made visible only by the phantom touch of dark energy. This turns the problem on its head. The anomaly is no longer a feature of the early universe, but a map of the intervening universe. It's a form of cosmic tomography using the ancient light as a backlight to reveal invisible structures standing in the foreground. In 2004, when astronomers first seriously proposed this idea, it was a tantalizing but unproven hypothesis. The first most obvious question was a simple one. If we point our telescopes in the direction of the cold spot, do we actually see a super void there? Is there a giant hole in the distribution of galaxies sitting exactly where it needs to be to create this effect? The theory was beautiful, logical, almost perfect. But cosmology is not a discipline of pure reason. It is a science of observation. The search for this cosmic desert, the so-called Eridanus supervoid, would require immense surveys mapping the locations of hundreds of thousands of galaxies in 3 dimensions to see if there truly was a great emptiness staring back at us. The stakes were immense. If confirmed, it would not only solve the riddle of the cold spot, but also provide stunning independent evidence for the existence of dark energy itself. The shadow of the void would illuminate the greatest mystery of our time. But if the void wasn't there, or if it wasn't large enough, then we would be back where we started alone, with an anomaly that defies all conventional explanation. The hunt was on. And so began one of the most audacious projects in modern cosmology, an attempt to chart the invisible to survey the darkness. The theory was a tantalizing ghost, a whisper in the mathematics. It suggested a colossal void, a gravitational valley could carve its chilling signature into the universe's oldest light. But to prove it, we had to move beyond elegant equations and simulations. We had to build a map not of the sky as a flat 2-dimensional tapestry, but of the cosmos as it truly is, a vast 3-dimensional ocean of space and time. The challenge was almost incomprehensible in its scale. Imagine trying to find a single, specific, unusually large air bubble hidden somewhere within the entire volume of Earth's oceans. You can't just look. The bubble itself is transparent. You can only infer its presence by meticulously mapping the location of every single fish, every plankton, every bit of life around it. Only by seeing where the life isn't can you begin to trace the bubble's ghostly outline. Our task was the cosmic equivalent of this, but staged on a canvas billions of light years wide. The life we were looking for was galaxies. And the bubble was a potential supervoid of staggering proportions. The target was a specific patch of sky in the southern celestial hemisphere in the direction of the constellation Eridanus the River. It was from this unremarkable region that the cold spot's anomalous chill emanated. Our quest was to peer deep into this cosmic river to see if its banks were hiding a vast empty basin. To do this, we couldn't rely on a simple photograph. A picture, no matter how beautiful, collapses 3 dimensions into 2. It tells you where a galaxy is in the sky, but not how far away it is. A bright galaxy could be small and close, or it could be a titanic city of stars very, very far away. Without that crucial 3rd dimension depth distance, we would be hopelessly lost, unable to distinguish a true void from a simple chance alignment of fewer galaxies in our line of sight. The key that would unlock the universe's 3rd dimension was light itself, and a fundamental property woven into the expanding fabric of space-time redshift. As the universe expands, it stretches everything within it, including the waves of light that have travelled across eons to reach our telescopes. Light from a distant galaxy is stretched towards the red end of the spectrum, and the amount of this red shift is a direct, reliable measure of its distance. The greater the redshift, the farther the galaxy and the further back in time we are looking. By capturing a galaxy's light and splitting it into its constituent colours, its spectrum, we could read its cosmic address with astonishing precision. It was this principle that would allow us to become cosmic cartographers. The plan was simple in concept, but Herculean in execution. We would point our most powerful telescopes towards the Eridanus region and systematically measure the redshift of every single galaxy we could find one by one by one. Each measurement would be a single pinprick of light on a 3-dimensional map, a solitary data point in an otherwise empty volume. By collecting hundreds of thousands, even millions of these measurements, a picture of the underlying structure of the universe would slowly emerge from the noise. We weren't just taking a picture. We were conducting a cosmic census, building a skeletal framework of the cosmos galaxy by painstaking galaxy. This monumental undertaking is known as a galaxy redshift survey. It is a process of immense patience and technological sophistication. At observatories perched on remote, arid mountaintops far from the glare of city lights, the work would begin each night as dusk bled from the sky. Inside the dome, a telescope, a marvel of engineering, would slew towards its target coordinates. But its eyepiece was not for a human eye. Instead, the focused light was funneled into an instrument of profound power, a multi-object spectrograph. At the heart of this system lies a precisely drilled aluminum plate. Each tiny hole in the plate corresponds to the exact position of a galaxy in the field of view. Into each of these holes, a robotic arm painstakingly plugs a delicate fibre optic cable. Hundreds of these fibres transform the plate into a robotic octopus, its tentacles reaching out across millions of light years to capture the ancient light of distant star systems. Each fibre sips the faint travel-worn photons from its designated galaxy and channels them away from the telescope into the spectrograph itself. Inside this complex machine, a series of prisms and gratings performs a kind of cosmic alchemy, splitting the feeble composite light from an entire galaxy into its rainbow spectrum. This spectrum is a barcode rich with information. Dark lines, called absorption lines, slash through the colours, revealing the chemical elements present in that galaxy's stars and gas. But most importantly, the entire pattern of lines is shifted. By comparing this shifted pattern to a reference spectrum created in a laboratory on Earth, astronomers can measure its redshift with unerring accuracy. This process is repeated for hundreds of galaxies simultaneously every single night. The data flows a torrent of numbers, each one representing a galaxy's distance, a single piece of an impossibly large puzzle. Projects like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey became the great engines of this new cartography. They were marathons, not sprints lasting for years, surveying vast swathes of the sky with relentless automated precision. Night after night, the observatories drank in the starlight, while teams of astronomers and data scientists processed the deluge of information. Slowly, painstakingly, the map began to take shape. On computer screens across the world, a new vision of the universe was being born. It was not the random uniform spray of galaxies one might expect. Instead, what emerged was a breathtaking, intricate structure, a cosmic web of unimaginable scale. We saw for the first time the true architecture of the cosmos. Galaxies were not islands. They were bound together by gravity into immense glittering filaments, great rivers of stars and dark matter flowing through the void. Where these filaments intersected, they formed dense, brilliant nodes, superclusters, cosmic metropolises teeming with thousands of galaxies. It was a structure both ordered and chaotic, a delicate glowing foam stretching across the observable universe. And just as the theory predicted, the spaces between these glowing structures were not empty. They were voids, vast, dark and profoundly empty regions where the cosmic web had been stretched thin, leaving behind immense bubbles of near-nothingness. The surveys confirmed that our universe was mostly composed of these great deserts. The glittering filaments and clusters were merely the luminous shores of an immense cosmic ocean of dark. With the cosmic web now charted in unprecedented detail, the team of astronomers led by Lawrence Rudnick and Shay Brown turned their full attention to that one specific naggingly cold patch of the sky. They drew a virtual cone into their new three-dimensional map, its point at Earth, its base expanding outwards in the direction of Eridanus. This was the search zone. If the theory was correct, somewhere along this line of sight, the map should reveal an anomaly, a region conspicuously devoid of galaxies, a hole in the universe. The anticipation was palpable as they began to populate this volume with their hard-won data. Each galaxy was a point of light, its position precisely known. One point appeared, then another. A small cluster here, a faint filament there. The numbers trickled in, building the picture layer by layer, deeper and deeper into space, further and further back in time. They pushed past our local galactic neighbourhood beyond the Virgo supercluster. They mapped the structures out to a distance of 500 million light-years, then a billion. The cosmic web continued to unfold its familiar pattern of filaments and voids. But as their search cone penetrated deeper into a region between 6 and 10 billion light-years away, something began to change. The data points grew sparse. The familiar comforting glitter of galaxies began to thin out. The filaments seemed to fray the clusters to evaporate, It was as if they were flying through the cosmic web and had suddenly emerged from a dense, foggy shoreline into a region of shocking, unexpected clarity. There were galaxies, but far, far fewer than in any other direction they had mapped. The density of matter plummeted. What they had found was not just another void. The standard voids discovered by the surveys were typically 100 million light-years across, impressive but not unusual. This was something else entirely. As they continued to plot the data, the sheer scale of the emptiness became staggering. It was a continuous cavernous region of space and underdense chasm, stretching for nearly 1.8 billion light-years. It was a structure so vast it beggared all comparison, 1 billion trillion times the volume of our own Milky Way galaxy. For a moment, some of the scientists thought it had to be a mistake, an error in the data, a flaw in the software, a blind spot in the survey. But they cross-referenced their findings with other surveys, including radio telescope data from the NRO VLA Sky Survey, which maps hydrogen gas instead of starlight. The result was the same. The radio sources, which traced the locations of active galaxies, also showed a dramatic dip in this exact region. The void was real. They had discovered a supervoid, a monster, one of the largest structures ever identified by humanity. In the dry language of the scientific paper, it was designated the Eridanus supervoid. But in the hearts of those who found it, it was something far more evocative. It was a wound in the fabric of the cosmos, a profound gravitational desert where for billions of years the relentless pull of gravity and surrounding regions had siphoned matter away, leaving behind an immense expanse of deepening nothingness. It was a place where the universe itself had grown thin. Here was a structure with enough gravitational influence, enough sheer emptiness, to potentially leave the kind of imprint they were looking for on light passing through it. The final electrifying step was to see if the monster matched the footprint. The team took their three-dimensional map of the newly discovered supervoid and projected its two-dimensional silhouette onto the sky. Then they took the now infamous map of the cosmic microwave background from the WMAP satellite with its inexplicable cold spot glowing in false colour blue. They laid one map over the other, and the fit was perfect. The location, the size, the orientation, it all aligned. The heart of the Eridanus supervoid, the deepest, most empty part of that colossal chasm, sat squarely undeniably in the centre of the CMB cold spot. It was a breathtaking moment of scientific synergy, the kind of discovery that researchers dream of. For the first time, there was a tangible physical object, or rather a lack of one, that could be directly linked to the most defiant anomaly in our picture of the early universe. The ghostly fingerprint on the baby picture of the cosmos now had a prime suspect, a colossal invisible culprit hiding in plain sight. The excitement was electric. It felt like the closing of a great cosmic case file. The supervoid theory, once a speculative piece of elegant mathematics, now had powerful observational evidence to support it. The integrated Sachs-Wolf effect, that subtle, gravitational theft of energy, was no longer just an idea. It was a mechanism with a place to happen. Here was the giant gravitational valley perfectly positioned. Here was the reason for the cold. For a dazzling moment, it seemed the mystery was solved. Observation and theory had converged in a stunning confirmation. We had stared into a cosmic anomaly, and by mapping the darkness had found a hole in the universe staring back. The Eridanus supervoid was the smoking gun, the missing piece of the puzzle, a beautiful and simple explanation for a deeply troubling problem. But in cosmology, as the data grows more precise, and the questions more refined, the simplest answers are rarely the whole story. The celebration of this perfect alignment would prove to be short-lived, as a new, even more perplexing layer of the mystery was about to unfold. For a breathtaking moment, it seemed the case was closed. The puzzle pieces fit with an almost preternatural neatness, a colossal wound in the cosmic web perfectly aligned with that inexplicable chill in the infant universe, the Eridanus supervoid. It was the smoking gun, the culprit hiding in plain sight for 13 billion years. Science, it appeared, had triumphed once more, replacing a profound anomaly with a satisfying, elegant explanation grounded in the known laws of physics. The integrated Sachs-Wolf effect, once a subtle theoretical prediction, had seemingly found its grandest stage, with photons of ancient light losing just enough energy as they traversed this gravitational valley to create the blemish we see today. The mystery we thought was solved. We had found the source of the cold, and yet in science the most elegant solution is rarely the final word. It is merely the next hypothesis to be placed upon the anvil of scrutiny, to be hammered by skepticism, data, and relentless testing. As the initial wave of excitement crested and broke, a new tide of inquiry began to rise, carrying with it a host of difficult, inconvenient questions. The supervoid was there, its existence confirmed by multiple surveys, a vast and undeniable emptiness. But as cosmologists began to model the crime scene with greater and greater precision, a troubling discrepancy started to emerge. The culprit was at the scene, but its capabilities seemed to fall short of the crime committed. The cold, it turned out, was simply too cold. The numbers didn't add up. The disconnect lies in the delicate nature of the gravitational mechanism itself. The integrated Sachs-Wolf effect is a whisper, not a shout. It is a subtle tax levied on light by the stretching of the universe. For it to carve out a depression in the cosmic microwave background, as deep and broad as the cold spot the void responsible would need, to be an abyss of almost unimaginable scale and emptiness. It would have to be a truly exceptional feature, a profound deviation from the cosmic average. The Eridanus supervoid is certainly immense, a staggering billion light-years across. It is profoundly underdense, a region where the great tapestry of galactic structure has been worn impossibly thin. But was it impossible enough? Was this chasm in space-time truly deep enough to account for the entirety of that 100 microkelvin temperature drop? To answer this, scientists turned from their telescopes to their most powerful theoretical tool, the universe in a box. They unleashed the full power of supercomputers' machines capable of performing quadrillions of calculations per second to simulate the evolution of the cosmos. These are not mere animations. They are rigorous, self-contained universes born from the initial conditions laid down by the Big Bang. Within these digital realms, virtual dark matter clumps together under its own gravity, pulling in gas to ignite the first stars and forge the first galaxies. Filaments weave themselves into a cosmic web, and in the spaces between voids expand like cosmic bubbles driven by the relentless push of dark energy. Over thousands of simulations, cosmologists could create thousands of different cosmic histories, each one a statistically plausible version of our own universe, complete with its own microwave background. The goal was simple, yet monumental, to see if a universe like ours naturally produces a feature like the Eridanus supervoid, and if that feature in turn naturally produces a signal like the CMB cold spot. It was a grand dress rehearsal for cosmic history, a way to test if the suspect's story held up under cross-examination. The simulations were run, the virtual skies were generated, and the results began to pour in. And they were profoundly unsettling. While the simulations could certainly produce massive supervoids, and those supervoids did indeed leave cold imprints on their CMBs through the ISW effect, they almost never produced a combination as extreme as the one we observe in our own sky. A void of Eridanus' size might appear, but it would typically create a cold spot only half as cold as the real one. A spot as cold as ours might flicker into existence, but it would usually be caused by a void far larger and emptier than the one we've actually measured. The alignment was there, but the magnitude was wrong. It was like finding a suspect's footprint at a crime scene, only to realize the print was 2 sizes too small. The simulations were telling us that, according to our best understanding of cosmology, the standard lambda CDM model, the Eridanus supervoid, as we currently measure it, is simply not gravitationally potent enough to be the sole author of the cold spot. It could account for perhaps 10, maybe 20% of the temperature drop. A significant contribution, yes, an accomplice, almost certainly. But the lone villain? The simulations screamed no. This created a vexing statistical tension. The cold spot itself is a 3 sigma anomaly, a 1 in 1,000 fluke if it's just a random temperature fluctuation. But the prospect of a standard void creating such an extreme effect was even less likely, pushing the odds into the realm of 1 in 10,000 or worse. We had seemingly replaced one improbable event with an even more improbable explanation. This led to a fierce and fascinating debate that cut to the very core of how we practice cosmology. The community split not into believers and non-believers, but into different schools of thought on where the discrepancy might lie. One camp argued that the problem was not with the theory, but with our observations. Mapping a three-dimensional void 1 billion light-years across is an epic feat of cosmic cartography, but it is fraught with uncertainty. We are trying to chart a region of near-nothingness defined by the absence of things we can see. Our measurements of its depth and its precise boundaries are based on counting galaxies across vast distances, a process susceptible to statistical noise and survey limitations. Perhaps they argued the Eridanus supervoid is far emptier than our current maps suggest. Maybe our surveys have missed its true dark heart, a core so profoundly vacant that its gravitational influence is far stronger than our models predict. This spurred a new generation of observational campaigns, using more powerful telescopes and more sophisticated techniques to drill down into the void structure. Surveys like the Dark Energy Survey began to meticulously chart the galaxies in that direction of the sky, aiming to produce a far more detailed high-resolution 3D map of the void's topography. The challenge is immense. You're trying to find the subtle gravitational contours of a valley by observing the sparse few lights that remain within it. Every galaxy's position and redshift must be measured with painstaking accuracy to build up a picture of the density field. It's akin to mapping the entire floor of the Pacific Ocean by observing only the handful of ships sailing upon its surface. The ongoing work is a testament to scientific persistence, a refusal to accept the simulation's verdict without first challenging the observational evidence it was built upon. If the void could be shown to be deeper, the explanation could perhaps be salvaged. But another camp of scientists looked at the same discrepancy and drew a radically different conclusion. They proposed that the problem wasn't a single measurement error, but a fundamental oversimplification of the void structure. What if we were looking at the Eridanus supervoid as a single monolithic cavern in space, when in reality it was something far more intricate, something our simulations of smooth, idealized voids were failing to capture? Perhaps the cold spot isn't caused by one gargantuan void, but by a more complex labyrinthine network of interconnected underdensities. Imagine not a single hole, but a structure like cosmic coral, or a sponge, a chain of smaller voids stacked one behind the other along our line of sight. This is the void in void, or multiple void hypothesis. In this scenario, a photon of light leaving the surface of last scattering doesn't just cross one gravitational valley, it traverses a whole mountain range in reverse. As it enters the first void, it gains a little energy. Before it can pay that energy back upon exiting, it enters the next void in the chain, then the next, and the next. Each void contributes its own small gravitational push, its own subtle ISW tax. Alone, none of these smaller voids could create a significant temperature drop, but together their effects could cascade, their cumulative gravitational influence amplified, creating a signal far stronger than any single void of the same total volume could produce. It transforms the problem from finding one impossibly deep chasm to finding a fortuitous alignment of several more common, shallower ones. This idea is compelling because it reflects the messy hierarchical nature of the cosmic web itself, which is not made of simple spherical bubbles, but of complex interlocking structures. Investigating this requires even more detailed mapping, looking not just for a large-scale absence of galaxies, but for the subtle bridges and walls that might separate smaller voids within the larger superstructure. Recent analyses of galaxy distribution in that region of the sky have hinted at just such a complex topography. Some studies suggest the presence of at least 3 or 4 distinct smaller voids nestled within the larger Eridanus region, arranged almost perfectly along our line of sight. This configuration remains statistically rare, a cosmic coincidence of the highest order, but perhaps a more physically plausible coincidence than the single ultra-massive void required by the simpler model. The scientific process is laid bare in this struggle. It is a dynamic, evolving conversation between observation theory and simulation. The initial clean discovery of the supervoid has given way to a murkier, more complicated reality. Each new layer of data, each more powerful simulation, doesn't simplify the picture, but adds new depths of nuance and uncertainty. The intransigent coldness of the anomaly resists our attempts to explain it away with the tools we have. The supervoid, which once felt like the final chapter of the story, now appears to be merely the opening of a more complex and perplexing act. Its presence is undeniable. Its gravitational fingerprint is all over the scene of the crime. But the evidence now suggests it could not have acted alone. We find ourselves in a state of profound and exciting ambiguity. The elegant standard model explanation is cracking under the immense pressure of precise data. Is the Eridanus void a single uniquely empty abyss whose true nature still eludes our telescopes? Or is it a complex gravitational echo chamber, an accidental alignment of multiple voids, whose combined effect is greater than the sum of its parts? Or more tantalizingly, is the discrepancy pointing towards a fundamental flaw in our understanding? The resilience of the cold spot, its refusal to be fully explained by this colossal hole in the universe, forces our gaze outwards towards the fringes of cosmological thought. It compels us to reconsider possibilities that once seemed too exotic, too speculative. Because if this void, one of the largest structures ever discovered by humanity, is not enough to solve the puzzle, then the true answer must be something else entirely. The ghost in the cosmic machine remains at large, and its chilling presence suggests that the universe may be stranger and more mysterious than we ever dared to imagine. The debate had reached an impasse, a chasm of uncertainty separating a colossal void from an inexplicable cold. On one side, a plausible, elegant theory grounded in the known laws of physics. On the other, a chillingly precise measurement from the dawn of time that refused to fully cooperate. For decades, we could only circle this cosmic mystery, armed with calculations that were by necessity approximations of an impossibly complex reality. We could estimate the gravitational potential of the Eridanus supervoid. We could model the integrated Sachs-Wolf effect with broad strokes, but the universe is not painted in broad strokes. It is an intricate, evolving masterpiece of unimaginable detail, where the subtle gravitational whispers of a billion galaxies can conspire to alter the journey of a single photon. To truly test the connection, to put the supervoid on trial as the cause of the cold spot, we had to move beyond mere calculation. We had to do something that was until very recently the exclusive domain of gods. We had to build a universe, not with stars and gas, but with mathematics and light. We needed to construct a digital cosmos in a box, a sprawling simulation so vast and so meticulously detailed that it could faithfully replicate the 14 billion-year saga of cosmic evolution. This is the frontier where cosmology and supercomputing merge into a singular, formidable tool of discovery. Inside the humming cores of the world's most powerful machines, we can now forge these virtual realities. We begin not with a void, but with a near-perfect uniformity mirroring the state of the universe as mapped by the Planck satellite. We seed this digital primordial soup with the tiniest quantum fluctuations, the almost imperceptible variations in density that were the ancestors of everything we see today. From there, we press play. The code, a symphony of algorithms embodying our deepest understanding of physics, takes over. Gravity, the silent sculptor, begins its work immediately. We watch as the invisible filaments of dark matter, the cosmic scaffolding upon which everything is built, begin to coalesce. Over billions of simulated years, these filaments thicken, drawing in more and more matter, knotting together at junctions where galaxy clusters will one day blaze into existence. Simultaneously, the spaces between these filaments are stretched and evacuated, giving birth to the great voids. But this digital genesis is far more than a simple gravitational collapse. To be accurate, it must contain the universe's deepest secret, its most profound mystery, dark energy. We have to inject this ethereal repulsive force into every cubic centimetre of our simulated space. It is a constant accelerating pressure, pushing against gravity's pull, a cosmic engine driving the expansion of the universe ever faster. Getting this ingredient right is paramount because the entire integrated Sachs-Wolf effect, the very mechanism we are trying to test, is a direct consequence of the titanic struggle between dark matter's desire to clump and dark energy's insistence on pushing everything apart. Without dark energy, a photon's journey through a void would be a zero-sum game. The energy it gains upon entering would be perfectly cancelled by the energy it loses upon exiting. It is only because dark energy stretches the void while the photon is inside that the cancellation fails leaving the photon measurably weakened, its light redshifted, appearing to us as a spot of cold. Our simulation must capture this delicate evolving balance with perfect fidelity. Yet even a perfect physical model is not enough. A simulation that evolves in isolation is just a beautiful piece of fiction. To transform it into a powerful scientific instrument, it must be anchored to reality. It must look like our universe, with its unique and particular arrangement of structures. This is where the painstaking work of galaxy surveys becomes the key that unlocks the entire endeavour. Astronomers have spent years meticulously mapping the heavens, charting the precise three-dimensional positions of millions of galaxies. Projects like the Dark Energy Survey have peered deep into the southern sky, building an unprecedented atlas of the cosmic web in the exact direction of the cold spot. This real-world map, a stunning achievement of observational astronomy, becomes the ultimate constraint for our simulation. We feed this data, this ground truth, into the computer. We tell our model, whatever you do, however you evolve, the final state of your digital universe, at this present moment must place the Eridanus, supervoid, and its surrounding structures right here. The simulation must end with a cosmic web that is a statistically perfect match for the one we observe through our telescopes. With these constraints in place, our digital universe is no longer a generic cosmos. It is a bespoke replica of our own cosmic neighbourhood, a dynamic and evolving ghost image of the very space between us and the afterglow of the Big Bang. Now the true experiment can finally begin. We can release the photons. Not one, not 1,000, but millions of virtual CMB photons are fired from the far side of our simulated box, their starting point, representing the moment of last scattering their light pristine and untouched. They begin their 13 billion year journey towards our virtual telescope. We program them to travel to feel the pull of gravity from every simulated dark matter halo, to be bent and deflected by the warping of space-time. And then we direct them straight into the heart of our carefully reconstructed Eridanus supervoid. We are no longer guessing at its depth or its profile. We are using the most accurate data-driven model ever created. You can almost feel the journey. As a photon approaches the edge of the void, it begins to fall inward, surfing down the shallow gravitational slope. Just as the ISW effect predicts, it gains a tiny burst of energy, a subtle blue shift that makes it infinitesimally hotter. For millions of years it traverses this immense emptiness, a region where the pull of gravity is weaker than anywhere else in the cosmos. But all the while, the simulation's dark energy is at work. The void is expanding, stretching its gravitational well, becoming even shallower than it was when the photon first entered. The climb out is now a steeper, more arduous task than the fall in. The photon struggles up the gravitational slope, but the hill has grown behind it. It expends more energy climbing out than it gained falling in. This is the critical moment, the transaction that lies at the heart of the entire hypothesis. As it finally emerges from the far side of the void, the photon is left with an energy deficit. It is weaker, redder, colder. The computer tracks this energy loss for every single one of the millions of photons that pass through the simulated void. It builds a map not of the void itself, but of the shadow it casts on the CMB light passing through it. This is the moment of truth where a decade of theoretical work, observational astronomy, and computational power converges on a single crucial image. The virtual telescope in our simulation produces its own map of the CMB sky. We filter out all the other effects, isolating only the temperature change caused by the supervoid. And we see it. A faint, subtle patch of blue appears on the screen, centered exactly where the void was placed. The simulation has worked. The integrated Sachs-Wolf effect, driven by a data-constrained supervoid in a universe filled with dark energy, does indeed produce a cold spot. A wave of vindication washes over the research teams. The fundamental physics holds up. A supervoid can and does leave a cold imprint on the cosmic microwave background. But then comes the second, more sober question. It is the question that defines the climax of this entire scientific drama. We know the simulation creates a cold spot. But is it the cold spot? We place the simulated data side by side with the real map from the Planck satellite. We compare the discovery with the mystery that spawned it. The location is a perfect match. The general shape, a large diffuse cooling, is also strikingly similar. The theory is undeniably on the right track. But then we look at the magnitude, the sheer intensity of the cold. The actual CMB cold spot is a chilling 150 microkelvin colder than the cosmic average. It is a profound deviation, a true statistical outlier. The cold spot generated by our most sophisticated, most realistic simulation to date is significantly weaker. Depending on the precise parameters of the model, the simulated cooling typically accounts for a drop of somewhere between 20 and 50 microkelvin. It is a measurable, significant contribution, far more than random chance could explain. It confirms that the Eridanus supervoid is a real and important piece of the puzzle. But it is not the whole puzzle. A gap remains. An unnerving, persistent gap between what our best models of the universe can produce and what the universe itself is showing us. Even with a void of this colossal scale, the known physics of the integrated Sachs-Wolf effect seems to fall short. It cannot by itself generate the full shocking coldness of the anomaly. This result, now replicated by multiple independent research groups using different codes and refined data, has become the new scientific consensus. The Eridanus supervoid is a major contributor to the cold spot, perhaps the primary one. But it is not the sole culprit. The simple, elegant explanation that we had hoped for has proven to be incomplete. The void is part of the story, but it is not the entire narrative. This realization is not a failure, but a profound success. It has moved us from a state of speculation to a state of quantifiable mystery. We now know the size of our ignorance. We can measure the portion of the cold that remains unexplained. The question has transformed from, is the void responsible, to, what else is happening in that patch of sky? This new, more nuanced question is driving the next generation of cosmic explorers. The simulations have shown us the limits of our current knowledge, and to push beyond those limits we need even better data. We need to map the Eridanus supervoid and the surrounding cosmic web with a level of precision that was once unimaginable, and the tools to do so are right now coming online. The Vera C. Rubin Observatory, perched high in the Chilean Andes, will soon begin a decade-long survey of the southern sky, cataloguing billions of galaxies and providing a map of the universe of unprecedented depth and resolution. Its data will allow us to refine the shape and profile of the void, to search for any smaller, denser structures within it that might complicate the gravitational landscape, or to confirm that it is indeed as empty as we believe. From space, the Euclid and Nancy Grace Roman space telescopes will chart the cosmic web over vast swathes of the sky, using subtle distortions in the shapes of distant galaxies, a phenomenon known as weak gravitational lensing, to map not just the visible matter, but the invisible scaffolding of dark matter itself. These forthcoming deluges of data will be poured back into our computational models, making them ever more faithful to reality. They will allow us to test more subtle hypotheses. Perhaps the void is not a simple spherical emptiness, but possesses a more complex elongated shape that alters the photon's path in unexpected ways. Perhaps it is aligned with other smaller voids, their cumulative cooling effect adding up to something greater than the sum of their parts. Or perhaps the influence of dark energy itself is not as uniform as we assume, behaving differently inside these vast underdense regions. Each of these possibilities can be programmed and tested, each simulation another step towards closing that explanatory gap. We are entering an era where our virtual universes will become nearly indistinguishable from the real one, allowing us to finally isolate the true nature of the cold spot's lingering chill. So we find ourselves at a precipice, looking out across a landscape of incredible progress and tantalizing mystery. The grand cosmological simulation, our most powerful tool for deciphering the universe's structure, has given us a partial yet profound answer. It has told us that the great void in Eridanus is undeniably implicated in the sky's greatest anomaly. It has validated the intricate dance between dark matter and dark energy that produces the integrated Sachs-Wolf effect. But it has also, with chilling clarity, shown us the limits of that explanation. It has left us with a residual cold, a signal that cannot be accounted for within our standard, extraordinarily successful model of cosmology. Science has successfully peeled back one layer of the mystery, only to reveal another deeper one beneath. The question is no longer whether the void is the cause, but whether the physics we use to model it is the complete story. Something is missing, and if that something is not a flaw in our maps or an undiscovered complexity in the cosmic web, then we are forced to confront a far more unsettling possibility. Perhaps the missing piece is not in the void at all, but in the very laws of the cosmos we thought we understood. And so we find ourselves here at the edge of that colossal chasm in the cosmos. We have journeyed from a single, inexplicably cold patch of light in a map of the infant universe, a faint blue stain on the masterpiece of creation, all the way to this magnificent soul-stirring emptiness. The path connecting that first light to this present darkness has been one of the great detective stories of modern cosmology, a pursuit that has forced us to confront the very architecture of reality. The Eridanus supervoid, our prime suspect, is more than just a potential answer to a persistent cosmic riddle. It represents a profound shift in our perception of the universe itself. We once saw the cosmos as a brilliant tapestry of stars and galaxies, with darkness simply being the thread holding it all together. But the cold spot investigation has taught us that the darkness, the void, is not passive. It is an active, dynamic, and powerful agent in the cosmic story. The search for a solution has compelled us to look not at the grand celestial cities, but into the vast, unlit wilderness between them. And in doing so, we have discovered that the universe is shaped as much by what isn't there as by what is. This entire intellectual odyssey has stretched the boundaries of our understanding of cosmic structure formation far beyond its previous limits. Before the cold spot demanded our attention, our models of the cosmic web, that intricate filigree of galaxy clusters and filaments, were robust, but they primarily celebrated the great concentrations of matter. They were stories of gravitational triumph of matter, pulling itself together against the relentless tide of cosmic expansion. The supervoid hypothesis forced a reckoning with the other side of that story, the story of gravitational defeat. It compelled us to model with far greater precision the large-scale evacuation of matter to understand how these immense gravitational valleys are carved out over eons. It's one thing to simulate a galaxy cluster, a glittering metropolis of gravitational attraction. It's another thing entirely to accurately simulate a region of space over 1 billion light-years across, from which matter has been systematically banished, leaving behind a profound and gravitationally feeble desert. We have had to refine our simulations to sharpen our theoretical tools to account for an entity whose defining characteristic is its astonishing lack of characteristics. In grappling with the scale of this emptiness, we've learned more about the delicate balance of forces that sculpts the universe. We've come to appreciate that the cosmic web is not just a network of brilliant nodes, it is a yin and yang of structure and void, each giving meaning and definition to the other, a skeletal architecture where the spaces between the bones are just as crucial as the bones themselves. The cold spot, in its quiet rebellion against cosmic uniformity, made us listen to the silence. But perhaps the most startling revelation to emerge from this cosmic ghost hunt has been its intimate connection to the greatest mystery of all dark energy. The proposed mechanism, the integrated Sachs-Wolf effect, is not some esoteric footnote in cosmological theory. It is one of the very few direct observable windows we have into the behaviour of this phantom force that is relentlessly pushing our universe apart. Remember the journey of that ancient photon of light born in the fire of the Big Bang as it falls into the gravitational well of the supervoid. In a universe without dark energy, a static or decelerating universe, the energy it gains falling in would be perfectly cancelled by the energy it loses climbing back out. The photon would emerge unscathed, its temperature unchanged, leaving no trace of its passage on the cosmic microwave background. The cold spot, by this logic, simply shouldn't exist. Its very presence, therefore, becomes a powerful piece of circumstantial evidence for the universe's accelerating expansion. Because of dark energy, the supervoid is not a static valley. It is a valley whose slopes are actively stretching and shallowing out while the photon is passing through. This is the crucial twist in the tale. The photon, having fallen into a gravitational well of a certain depth, must then climb out of a well that has become shallower in the interim. It doesn't have to work as hard to escape. It leaves with a tiny surplus of energy, which should paradoxically make it appear as a hot spot on the CMB map. The fact that we see a cold spot has been the central nagging puzzle, suggesting that our understanding of the ISW effect or the void itself remains incomplete. Yet the very fact that we are forced to have this conversation to debate the subtle energy shifts of single particles of light over billions of years due to a stretching cosmic fabric is a triumph. The cold spot has transformed from a mere anomaly into a cosmic laboratory. It has become a testing ground where the grand sweeping theories of dark energy are forced to confront the granular reality of observational data. It is a magnifying glass held up to the most enigmatic force in nature, a force that will ultimately decide the fate of everything. Each new piece of data we gather on the Eridanus supervoid is not just a map of empty space. It is a clue in the case file of the universe's ultimate destiny, a whisper of the phantom hand that is pushing everything apart. This entire investigation has also been a masterclass in the intricate dance between matter and light, the two fundamental constituents of our visible universe. It's a story told across 14 billion years, a story of a single photon's epic journey. Imagine it again, a particle of light, a messenger from the dawn of time carrying a pristine record of the universe when it was just 380,000 years old. For billions of years, it travels an uninterrupted flight through an expanding, cooling cosmos. It witnesses the birth of the first stars, their violent death seeding the void with the elements of life. It skirts the swirling gravitational whirlpools of nascent galaxies and sails past the blazing infernos of quasars. Its path is a straight line through space-time, a testament to the universe's large-scale homogeneity. And then in the last few billion years of its journey, it encounters this anomaly, this yawning chasm where there should be galaxies. The delicate interplay begins. The photon is pulled in by the faint gravity of the matter at the void's edge, its wavelength compressing its energy, increasing infinitesimally. It traverses the immense emptiness, a ghost flitting through a haunted house a billion light-years wide. Finally it begins its climb out, pulled back by the gravity on the far side. And it is here, in this final leg of its passage, that the universe's deepest secret, its accelerating expansion, driven by dark energy, leaves its faint, almost imperceptible fingerprint. The light that finally reaches our telescopes is subtly changed, a traveller bearing a story etched into its very energy. It is a story of a cosmic robbery of energy, stolen by the stretching of space-time itself. The cold spot is the shadow left behind by that cosmic transaction. This narrative, this dance between a single particle of fossil light and the largest known structure in the cosmos, is a powerful reminder that we are not merely observers of the universe. We are participants receiving these ancient messages and piecing together the epic history they contain. We have learned that to understand the grandest structures we must follow the faintest trails. To map the unseen ocean of dark matter and dark energy, we must track the flight of the oldest light. The cold spot has been our guide, teaching us that every photon is a history book, every patch of sky a potential clue, and that the most profound truths are often written in the faintest of inks. It has underscored a fundamental principle of cosmology, that light is the ultimate cosmic scribe and matter, and energy are the ink with which it writes the story of existence, a story we're only just beginning to learn how to read. But for all the progress, for all the breathtaking insights, the explanation remains tantalizingly incomplete. The supervoid as we currently measure it seems insufficient. The integrated Sachs-Wolf effect it should produce appears too weak to account for the full shocking chill of the cold spot. This is not a failure, it is an invitation. It is the universe telling us that the story is more complex, more subtle, and infinitely more interesting than we first imagined. And so we stand on the cusp of a new era of discovery, preparing to launch a new generation of sentinels into the cosmic dark instruments, with the power to turn this compelling hypothesis into established fact, or to shatter it completely, forcing us back to the drawing board in a glorious return to the unknown. The next chapter of this story will not be written with elegant equations alone, but with the flood of data from new eyes on the sky. Behold the future, a future that is already taking shape in clean rooms and on remote mountaintops around the world. Soon the Vera C. Rubin Observatory, perched high in the Chilean Andes, will begin its decade-long legacy survey of space and time. It is destined to become the greatest celestial cartographer in human history. Night after night, its enormous eye will scan the heavens, mapping the positions and properties of billions of galaxies, creating a motion picture of the dynamic universe. For the cold spot investigation, Rubin is a game-changer. It will not just confirm the existence of the Eridanus supervoid, It will chart its topography with breathtaking precision. It will reveal the intricate substructures within it, the faint tendrils of dark matter that might still lurk in its depths, the subtle gradients in its galactic population. It will find not just one supervoid, but potentially hundreds, even thousands of them. For the first time, we will have a comprehensive catalogue of the universe's great deserts, allowing us to ask, is the Eridanus supervoid truly special? Or is it merely the largest of a common class of cosmic structures? With Rubin's data, we can stack the faint CMB signals from all of these voids, averaging them out to see if a statistically significant cooling effect emerges. This is the brute force approach, the power of big data brought to bear on one of cosmology's most delicate questions. The observatory will provide the definitive map against which all theories must be tested. Joining this quest is the European Space Agency's Euclid telescope, a detective specifically designed to hunt the very phantoms we have been discussing. Euclid's mission is to map the geometry of the dark universe. By measuring the shapes and redshifts of billions of galaxies, it will trace the influence of dark matter and dark energy through cosmic time with unprecedented fidelity. For the cold spot, Euclid offers a different, more nuanced perspective. It will provide not just a two-dimensional map of galaxies on the sky, but a truly three-dimensional reconstruction of the cosmic web, allowing us to understand the full volume and depth of the Eridanus supervoid. Its precise measurements will directly test the predictions of the integrated Sachs-Wolf effect, quantifying how the growth of structure is being suppressed by the accelerating expansion. Euclid will essentially feel the cosmic push of dark energy by observing its subtle stunting effect on the gravitational pull of matter. This will allow us to calculate with far greater certainty just how cold a spot a supervoid of this magnitude should be able to create. It will be the moment of truth for the conventional explanation, a direct confrontation between theory and observation in exquisite detail. And looking even further ahead, NASA's Nancy Grace Roman Space Telescope will open a panoramic window onto the cosmos that is hundreds of times larger than that of the Hubble Space Telescope. Roman is the wide-eyed wanderer designed to answer essential questions about dark energy exoplanets and infrared astrophysics. Its vast field of view will allow it to conduct deep, wide surveys of the universe, uncovering the largest structures and mapping the distribution of dark matter on immense scales. Roman's power lies in its ability to see both the forest and the trees. It can simultaneously study the detailed properties of galaxies within supervoids while mapping the void's overall structure and environment. This will help us understand the complete life cycle of these cosmic deserts, how they form, how they evolve, and how they interact with the surrounding cosmic web. It will provide the crucial context, the grand vision needed to place the cold spot and its associated void into their proper cosmological setting. Together, these three titans of astronomy, Rubin, Euclid, and Roman, form a triumvirate of discovery. They represent our collective resolve to map the darkness, to understand the unseen, and to finally definitively answer the question that has haunted us for decades. So where does this leave us as we stand here looking back at that faint cold anomaly? We are left in the best possible place for a curious species to be, with a beautiful, compelling story that is not yet finished. The cold spot has served its purpose magnificently. It has been a cosmic irritant, a grain of sand in the oyster of cosmology, that has forced us to produce the pearl of a deeper understanding. It has pushed our theories of structure formation to their limits, provided a unique arena for testing the nature of dark energy, and illuminated the profound connection between the universe's oldest light and its largest structures. The journey, regardless of the final destination, has been the reward. The supervoid hypothesis provides a framework of exquisite elegance, linking so many disparate pieces of the cosmic puzzle together into a coherent whole. Yet science demands more than elegance. It demands proof. Perhaps the next generation of telescopes will show with incontrovertible data that the Eridanus supervoid, combined with the subtle draining of energy by dark energy, is precisely the right shape, size, and emptiness to create the cold spot. The case will be closed, the anomaly will be explained, and it will stand as a glorious testament to the predictive power of our standard model of cosmology. It will be a universe that is strange and wonderful, but ultimately a universe that plays by the rules we have so painstakingly uncovered. But what if they don't? What if even with these new hyper-accurate maps the numbers still refuse to add up? What if the void is simply not enough? then we will find ourselves in a far more exhilarating landscape. We would be forced to confront the alternatives we have only dared to whisper about. Is the cold spot a bruise, a remnant of a collision with another bubble universe in the infinite foam of the multiverse? Is it a texture, a topological defect in the fabric of space-time, a scar left over from a primordial phase, transition in the first femtosecond of creation? Or is it something so alien we have not yet even conceived of the language required to describe it? That is the true magic of this quest. The cold spot has become a fulcrum upon which our entire understanding of the cosmos is balanced. Whichever way it tips toward a triumphant confirmation of our current theories, or toward a revolution that shatters them, we will be irrevocably changed. The great map of the cosmos is not yet complete. There are still regions marked, "Here be dragons," and we, with our insatiable curiosity and our ever more powerful eyes, continue to sail toward them, drawn by the siren song of the unknown, forever continuing our grand and noble quest to understand our place in the silent, star-dusted dark.